Yaghoob Farnam. I think Yaghoob received his PhD in Purdue University and now an assistant professor in Drexel University.
Thank you very much, Ingo, for the introduction. So I changed the topic a little bit here, and we're going to mainly be talking about the micro-capsulated phase change materials efficient for thermal energy management of concrete structures. And I'll try to provide some experimental result, how actually the efficiency that we're going to get. So the work has been done by my PhD student, Mohammad, Balapour, so all the credit goes to him. I did a little bit of contribution. And at the beginning, I was asked to prepare 15 minutes talk, but now I have to talk 25 minutes. So I put this slide there, what is phase change material? And so the idea of making a hot fudge ice cream, and this comes from a memory that I had with my nephew, that he loves ice cream with hot fudge, and he loves the hot fudge part of that, and he has to add like more hot fudge, so he was asking, add more hot fudge, and I said, come on, you're gonna melt the entire ice cream if I want to add more hot fudge on that. So the idea here is that the hot fudge could serve as a thermal source for ice cream, and that is the idea of PCM. So you could have some types of phase change materials. On the other hand, ice cream provides something like a thermal, like a sinking source for the hot fudge. So both of them actually, they're acting as a phase change materials in this case. So if you want to talk a little bit more scientific about what is phase change materials, it's just like some liquids or some solids, and we want to design the melting temperature for the different types of application that we want to use. So if you want to use it in cooling events, so what we do, we lower the temperature, and here actually we could use some types of liquid phase change materials, and as the liquid phase change materials, they go from liquid to solid, they're gonna release some heat, and we could use that heat to increase the temperature of the surrounding environment. We could use it all the way on the other side, like in the heating cycle, and in this case, if it's liquid and it goes from liquid to solid, then it's going to absorb heat from the surrounding environment. So you could actually cool down your concrete by using that. So you could store energy, or you could release thermal energy to the surrounding environment by using these phase change materials. So for releasing heat during cooling events, it's mainly like to keep the surrounding environment more warmer. It can be used for melting snow and ice. This has been one of the research that we've been doing for over the last 5 or 6 years, and we've been able to melt something about 5 to 6 inches of snow, enormous amount of snow, by using phase change materials in concrete pavement. Or you could use it in absorbing heat during heating events, and in this case we want to actually like cool down the concrete. In mass concrete, one of the big challenge that we have, it's the thermal heat release from hydration, and we want to mitigate that, so we could use phase change materials to absorb heat from cement hydration. So managing heat buildings, there are so many research going on in this case. We want to actually regulate the temperature inside the building, so we could save energy, electrical energy, to cool down or heat up the room inside the building. We could use it for self-healing pavement. This is one of the things that we've done, and this is one of the examples actually we did, large scale slab using phase change materials, no phase change materials, and this is with phase change materials, no phase change materials, and you see like we put something about 5 to 6 inches of snow, it could melt the entire snow there. But here we do get like icing. One of the things that I want to mention here is that we want to be very careful in the PCM design in our concrete. For different types of application, we want to use different types of PCM. The PCM that works for building, we cannot put it in pavements for snow melting. And the idea is that we want to have this phase change happening at a temperature close to snow melting temperature, which is 0 degrees Celsius. In buildings, the comfortable temperature is something about 22 to 23 degrees Celsius. So the PCM should be designed for that type of temperature. The other idea is, again, the mass concrete or pavements, that you have some types of like internal heat generation through hydration, or it might be some pavement that are exposed to very hot temperature, like in Arizona. And the idea is that as you have this heat released through the cement hydration, this PCM serves as a thermal reservoirs, and they could actually suck the energy, the thermal energy from surrounding environment, so you don't get that much of thermal cracking. So the question is that how we want to incorporate phase change materials inside concrete, and different types of methods. We will have different types of performance. We could put it very simple case. We put a pipe there. We could fill in the, and then we can cast concrete around the embedded pipe. And then we could fill in the PCM inside that. There are some advantages, some disadvantages of doing that. If you want to put pipe there, one of the things is that it's going to be very expensive. You have to be very careful how you want to transfer the heat from the PCM inside the pipe to the surrounding environment, because you don't have a good distribution of PCM or phase change materials inside the concrete. And it's going to be a little bit expensive. But some advantages is that these are some types of vessels, some types of like vascular system inside the pavement. So what you could do during summer, if you need a special type of PCM, you could actually put that type of PCM. During winter, if you want to change the PCM, you could change the PCM easily through this piping. The other idea is using porous lightweight aggregate. In this case, what you do, actually use the porous media as reservoirs for these phase change materials. The idea of internal curing that we have been using for a long time. And so what we do, we put this, we soak this lightweight aggregates inside PCM, and then we could actually store the PCM inside that. The third idea is just using capsules. And these are some capsules that are available in the market, and you could mix the capsules with your concrete, and you could actually get benefits from these phase change materials. But again, we have to be very careful in this case, and I'm going to mainly be focusing on encapsulated PCM, because during mixing, actually you could break them, or there are some challenges of using them. So one of the challenges that we have when you use encapsulated PCM. So we have some PCM inside some shell, and this shell could be made of melamine-based material or silica-based materials, different types of materials. The shell could be different. One of the problems that we get is the mechanical rupture. During the concrete mixing, we do have aggregate friction going on, and that might cause some types of breakage of the shell, and the PCM could leak out, causing some problem. The other problem that we have, and Afshin just briefly mentioned that, is the chemical dissolution. And you do have this shell. As we know, concrete environment, it's a high alkaline environment. We do have different types of ions, sodium ions, OH ions, sulfate ions. You might get some types of like chemical interactions between pore solution and the shell, and then you could have some deterioration, shell deterioration because of that. So again, in this case, you might have some leakage causing some problem in the system. So this is actually like the motivation, and actually when I started working with my PhD student, this was a question that he asked, and we decided, okay, we're gonna spend some time on that. Do we really get the energy that we designed for? We know the amount of PCM that we put it in, and we know the latent heat of fusion of the PCM. So if we expect X amount of energy, do we get X amount of energy? How much reduction do we get? This is one of the questions that we have. And another thing that Hingon just mentioned, the mechanical properties. So there is a balance. You want to increase the thermal properties, the thermal performance of PCM. You're going to have some reduction in the mechanical properties. And different methods, they're going to have different influences on that. So how much mechanical reduction that you want to accept by adding this little capsules inside your concrete, and because you want to actually provide some thermal, some heater or cooler inside that, but you want to get some types of mechanical reduction. What would be the trade-off over there? So to address that, we started doing some experiment. We started to look into that mixing speed, medium speed, fast speed, and slow speed. We started changing the PCM dosage inside the concrete to see like what would be the effect of that. And one of the things that I want to mention here, PCM, we just replace it by aggregate. So we get a portion of aggregate, then we add by volume the PCM inside that. So this is the way that we could incorporate PCM inside. So when I say 10% dosage of PCM, I mean that 10% of aggregate is replaced by volume, by PCM. And then the other question that we had, what would be the effect of sample size on the thermal performance of that? Smaller sample, they're going to behave totally different than larger sample. We're talking about thermal diffusion, thermal conductivity, which is dependent upon the distance of the heat transfer inside your system. So you have to be very careful. Larger sample, they're going to behave different than a smaller sample. And we wanted to see what is the main difference if we scale up the sample size. So we just use one type of PCM here because we didn't want to actually study the PCM type effect. So we used the paraffin oil, which was the melting point about 4 degrees Celsius. This is a really good PCM for snow and ice melting. This is again one of the research line of research that we're doing. And I'm gonna mainly talking on this type of graph. So let me explain it a little bit. This is a heat flow as a function of temperature. So as we decrease the temperature, we're going to get a phase change or like a change in a big peak or spike in the heat flow. And that spike or peak is actually a phase change formation, because any phase change, this is principal physical phenomenon, right? Liquid to solid, we have latent heat of fusion that should be released or absorbed. And that peak actually like the heat release. Okay, so if this heat release gets bigger, so you will have more energy inside your system. So this is a DSC, differential scanning calorimetry result of the PCM that we use. And so the PCM that we use had something about 155.4 joule per gram of latent heat of fusion inside that. And then we didn't change the water to cement ratio. That was not the goal of this research. Aggregate content, we kept it constant, 55%, and we started replacing that 55% by 5%, 10%, 15%, and 20%, and up to 30% replacement of the aggregate. And then we replaced it by using PCM. And then we had 3 types of mixing speed, 55, slow, medium, and fast. And we had some, we wanted to see the effect of aggregate and the mixing. So this is a picture of differential scanning calorimetry, and normally this is a very sensitive device for a small sample. You have to put something about like 5 to 20 milligram of sample. So we made our sample, and then we used the diamond saw. We cut slices out of that, 2 to 3 millimeter of a slice, and then we took a little bit of that, 15 to 20 milligram of the sample, very tiny sample. And then we put it inside this differential scanning calorimetry and look at the temperature profile of that. So if you look at the differential scanning calorimetry result, and again, this is heat flow as a function of temperature. So no PCM, no spike, no peak. So it's what we expected. If we add 10%, we're going to have a little bit of spike here, or the peak, and that is the heat release. If we add 30%, that peak is going to increase. And this is something that we expect. So what we could do, actually, we could go ahead and integrate that peak and find out the amount of latent heat inside that sample. And if we do that and we integrate the peak and find out the thermal energy or latent heat of fusion, this is the type of behavior that we're going to get. So this is the PCM dosage, so 5% off to like 30%. This is the latent heat of fusion, the area under that peak. If we look at that, DSC gives us some types of linear behavior, and this is what we expected. Nothing unusual about that. You increase the amount of PCM, you add more thermal reservoirs, so you're going to increase the amount of energy release in your sample. So nothing very complicated there. And effect of mixing speed, as we increase the mixing speed, we have lots of friction, and we could break actually our PCM. And this is what type of behavior? Linear reduction inside our sample. So this is something that we have to be very careful. The amount of mixing, the time of mixing, the speed of mixing, these are the things that we have to be very careful to that. So DSC is perfect. It's very sensitive device, and it's really good, right? But we're not dealing with 15 to 20 milligram of sample. We're dealing larger scale, inches of sample. So we wanted to see what would be the performance if we scale it up to something about like inches. And that is the thing that we started actually making a special type of calorimetry in our lab. And we called it longitudinal guarded comparative calorimetry, and or LGCC. And this is the work that we have done in collaboration with NIST, National Institute of Standards and Technology in the US. And the idea is that we want to have some types of like a steady state, one directional heat flow. So you could actually have some calculation. You could do some types of calculation to figure out the thermal heat release inside the sample. And then we want to be very slow. So here we're talking about like degrees per hour. So we change 4 degrees per hour. So it's a kind of long process because we want to be in a steady state. We have some assumptions here. And the idea is that we have this cold plate. We could change the temperature. We put our sample, which is about like 2 to 3 inches of sample that we put it inside. And then you do have 2 meter bars at the bottom and the top of the sample. And these are like standard meter bars. We use pyrostyrene, very expensive material. And we measure the temperature at different locations, 1, 2, 3, up to like 7 different locations. And then it goes through some types of calculation. We could back calculate, find out the amount of the heat flow as a function of temperature. But there are some assumptions here, some simplification, and we have to be very careful about that. But as we go slowly, we are very close to this steady state. So this could be a promising type of approach to do that. So we did that, and this is one of the results that we get from LGCC. Again, heat flow as a function of temperature, something similar to what we get from DSC. And as you can see, we do have that heat spike. And this is the cooling heating cycle. So this is a freezing part. This is the heating part. What we could do, we could actually go there, zoom in on that peak, and then could do some types of calculation, integration there, and we could find out the amount of heat release inside my sample. And here we're talking about 3 inches of sample. So if you look at that, no PCM, no spike, no peak there. And this is something expected. And again, with PCM, as we cool down the sample, we get heat release. And as we increase this temperature, we go back to the heating cycle, then you get some types of like storage there. So again, we could do the integration at the peak, the area of that peak. And this is the result that we get from LGCC, large scale. So something interesting actually like we observed when we scaled up our sample. At the beginning, when the amount of PCM is lower, we do get some types of like linear behavior. And again, when we increase the temperature, the dosage, and we are like over 20%, then the slope varies. So some types of like bilinear effect. So we want to be very careful. And this is maybe like partially coming from using large sample, or might be coming maybe partially from the assumption that we made in LGCC. But the type of behavior that we get here is type of like bilinear effect. So it might not be effective that you increase the PCM dosage too much. If you look at the mixing speed, again, we saw something similar to this, a bilinear effect. And again, here, it might be partially from LGCC testing protocol, or it might be because of the sample size. So we wanted to see the differences between DSC and LGCC in the smaller sample and the large sample, and see what would be the difference that here we get. So we did some types of extra calculation, and we normalized the amount of heat release. And this is the released heat calculated through LGCC or DSC divided by the expected. As I mentioned earlier, we know how much PCM we put it in, right? So we could have an idea. We could expect the amount of energy, the thermal reservoirs that we put it inside. So we could have an idea how much of that is effective. So if you look at the DSC result, something similar. As you increase the PCM dosage, we saw something about like 30% reduction in the thermal energy. So this was constant through all the percentage that we use. So we are missing 30% of the performance of the PCM that we put inside. If you look at the LGCC result or larger sample, and again, it's kind of like a flat plateau, and it's about like very good compatible with the DSC result. At some point, about like 17%, then we could get that we get that bilinear effect, and that is it's gonna deviate from the DSC work, and it might be because the inter effect of the amount of PCM that we put it in, and because we put lots of this reservoirs, this PCM inside the concrete, so you might have some interaction between them, so you don't get that much of effect at a larger dosage. If you look at the mechanical properties, this is the question that everybody asks. So when I go to, I have a talk, everybody asks, what would be the effect of adding this soft materials in mechanical properties? So this is control, and here we are increasing the dosage, compressive strength, and if this is the control, we have to be very careful. 50% reduction by adding 30% by volume. And this is 30% of the aggregate, not the entire concrete. So we replace 30% of the aggregate, we get something about 50% reduction of the entire concrete. So we have to be very careful. So there are some trade-off here. We add PCM soft materials, you lower the mechanical properties. You get some advantages in terms of like having some types of like reservoirs in the system, or the thermal performance that you do get, but in the mechanical part, actually you might face some problem. So just summarize what I talked about. So the goal of the research was to understand the thermal energy of the encapsulated PCM inside the concrete. And as I mentioned, that there are some challenges when you put microcapsules, because you could break them, you could have some chemical interaction, so you could actually like break the shell, so it might not be efficient. So we wanted to see what would be the efficiency. And going back to my title, are microcapsulated PCM efficient for thermal energy management of concrete structure? We have to be very careful. We have something about 30% reduction in the thermal performance. This is a minimum reduction that we get. It might be more than this. Mixing speed, we have to be very careful if you want to put PCM inside big trucks, and make pavement out of that. It's going to stay inside truck for 90 minutes. Mixing might break the shells. And there is, and at the end, the last point that I want to make, that there is a trade-off. There is an optimum dosage that we want to have. We want to have the thermal performance and mechanical performance at the same time. We don't want to add too much PCM and get lots of reduction in the mechanical performance of the concrete. So with that, I want to finish my talk here, and if there is any question, I would be more than happy to answer.